Okay, so welcome back. Let's continue discussing about macrocanonical and canonical ensembles. So this class is to be um as a continuation of the previous module lecture or whatever you want to say. I'm not going to repeat this. I just repeated it at the end of the last recording. What I'm going to start with, though till now we have been discussing about isolated systems, which means a box of gas, which cannot exchange energy with its surroundings, and is constant volume and fixed number of particles. Now, this room in which you are sitting is doesn't describe that system because the AC is running. And in this room, actually, there is also particle exchange in that gas particles are going out. It's going out of through the doors. But for the moment, let's assume, and we'll discuss that as well, but it'll take some time. But for the moment, let's assume that this room has a fixed number of particles and it is in contact with the heat reservoir. Okay. Here the AC is running, but let's assume there's no AC and this room has the ambient temperature as that of the city. So this room is exchanging heat. Some heat from Pune city is coming in, from the atmosphere is coming in, and sometimes the heat, a small amount of heat is going out. But you know that this room has an average certain internal energy, right? So let's take a system, an isolated system, as we were talking about in the previous class, which and a small part of that isolated system is the room, right? And this room is exchanging, there is a heat exchange with the city, which we call as the heat reservoir. And let's take the city itself to be an isolated system. That's just a simplification or an idea. Of course, Pune is in contact with Lonavala and all the neighboring cities, but of for the sake of developing the methods, and we'll see whether the methods work or not. Let's assume that you have a heat reservoir, the city, and the room is a small part of the heat reservoir, and there is an exchange of energy. So this room has a fixed number of particles and a fixed volume V, but energy is not fixed. Okay, so there is heat exchange, and this system and the microstates of this room where N is fixed, V is fixed, but it has different energies. That system is called a canonical ensemble. We'll come to it. So first, let's think of what the room is doing. Suppose at a certain point of time, okay, let's say for 1 second, just for the sake of it. This room has energy E1, volume V, number of particles is fixed, but the energy E1 plus the energy of the heat reservoir is fixed, is E0. Okay. At some other point, this room absorbs some more energy from the reservoir. So the energy of the reservoir decreases, the energy of the room increases, and it becomes E2. It has volume V and number of particles N, and E2 plus ER double dash, right? Because it has given out. So the reservoir has a different amount of energy. It's again fixed because we assume that the entire big uh, system is isolated. So we know how to work with isolated systems, right? And then later, this room gives out some heat to the reservoir. So so the reservoir has more energy, E double dash R, and the room has energy E3, where total is still remains fixed. Now remember, when this room has energy E1, it has a certain number of microstates, call it omega 1, accessible to it, right? And it can explore all these microstates. When it has energy E2, it has a different set of microstates, some of which might overlap, or well, the total energy has to be fixed. So it will have a different set of microstates available to this room. And similarly for E3. So this room with energy fluctuations has a much larger set of microstates available to it as the particles move around within this room, within a fixed volume, n particles, but sometimes they're taking a bit more energy, so that the sum of the kinetic energy is E1, sometimes it is E2, and sometimes it is E3. Yeah, so there's a different set of microstates because it's moving on a different hypersphere, if you like, right? With each different values of energy. So the total number of microstates that is accessible to this room, when it is able to exchange energy with the heat reservoir, is much more. So that's the first idea which I want you to take home. Furthermore, suppose this system has energy E1, okay, and this heat reservoir has energy ER dash. Now, if we just fix this state, then I mean, think about ensemble. So this heat reservoir has a certain large number of microstates which is available to the system omega r when it has energy ER dash, right? And for each of those microstates for the reservoir, the system can take a large number of other microstates. Suppose there's a particular configuration of particles in the heat reservoir, and correspondingly also momentum. Now, for that particular microstate, the particles in this room with energy E1 can rearrange themselves in many, many ways, both position and momentum. For another set of energy of the heat reservoir, suppose E2, again, this room will access a huge number of different microstates. Sorry, even with energy E1, suppose this heat reservoir was in a different microstate, fixed. Even then, the room your system can occupy a large number of different microstates, right? I mean, it might be in a different microstate. So the total number of microstates for the entire system, reservoir plus system, for each set of microstates, your system has a different set of microstates it can access. So the total number of microstates is a product of the two. Let's call it omega. Now the question you're going to ask that, okay, the system can exchange energy with the reservoir. What is going to be the average, what is going to be the room energy in equilibrium? Because it's possible that it gives up all the heat to the reservoir or takes a huge amount of heat from the reservoir. Under what conditions will the total number of microstates for the entire system be maximum? The entropy, right? For the whole entire system be maximum, because it will reach equilibrium when the total entropy is maximized. The total number of microstates is maximized. So the condition of equilibrium of heat exchange with fluctuations, right? Now there's heat exchange, there's fluctuations, because we are really talking about the microstate, is when the total number of microstates is maximized, and the condition for this maximization of the of reaching equilibrium, maximizing the number of microstates, will be, you will see that we'll calculate a certain quantity, and that we will identify as the temperature of the reservoir, and a similar quantity will be calculated for the system, and these two quantities, when they are equal, then the entire system will be in equilibrium, and that will identify as temperature. So the point is, it will, so this, the reservoir and the room will be in equilibrium with each other when a certain quantity, which we shall call the temperature and shall identify with the temperature, will be equal. So in this case, so now just taking the story around, assuming we have done the all the, what is it called, derivations and so on and so forth, this corresponds to this room, where this room is in contact with the heat reservoir and its temperature is the same, right? That is what you know from thermodynamics. But you can also get that from statistical physics. We'll calculate certain conditions of equilibrium when the entire omega is maximized, and that quantity, which will be equal in the two cases for the condition of maximum entropy for the entire system which is isolated, will turn out to have all the properties of the temperature. We will call it temperature to make a mapping with thermodynamics, right? But no, this is not but the probability. So, but now the system has the same temperature, but there can still be energy fluctuations. And the question is, how far will the energy fluctuations be? Because there is an exchange continuous, so some heat is going in and out and so on and so forth. The probability that the system, which is at T, V, and N, so this room is in, will define that this room is in at the same temperature as the heat reservoir, and if we can define a temperature, then we can define something called KBT, which will come. Then the KB came much later, or the exact value of KB came much later. It was slowly developed. I'm giving you the entire picture in whatever 45 minutes. So in this case, the system, the room with different, when it has different values, E1, E2, E3, the probability of accessing those microstates which have different values of energy E1, E2, E3 are different. In the previous case, all microstates were accessed with equal probability. In this case, I have missed out a minus sign here. The probability that the system with a fixed T, V, and N is going to access a microstate with higher energies, or any energy for that matter, it can be high or low, so the value of E could be high or low, is proportional to, as we shall show, e to the power minus E, where the minus is missing here, by KBT. Okay, so different sets of microstates will have different energies as it keeps exchanging with the heat reservoir, and now we are focusing only on the microstates of the room, of the system. We are interested in the properties of this room, and if energies with higher microstates with higher energy have lower probability of being accessed, and how much lower is proportional to e to the power minus E by KBT. Okay, so why differences? So basically, for a corresponding value of energy E1, there will be a large number of microstates, right? So each of those microstates will be accessed with a probability which is proportional to e to the power energy of that microstate by KBT. And if a large number of microstates have a different energy, each of those microstates will be accessed with probability e to the power minus e by kBt. But each of the microstates which have energy E, they are accessed with the same probability, proportional to e to the power minus e by kBt, right? So that's what I have written essentially here. And in general, one can generalize these particles to degrees of freedom, and they can arrange themselves in different ways in phase space to occupy different microstates, all with energy Es. This S is to remind you that we are talking about the system, which is this small subsystem, this room, if you like, and there's a reservoir. We're not focusing on the reservoir. And K is a particular microstate. So all microstates with energy system, a particular microstate of energy ESK have probability proportional to e to the power minus beta, where beta is 1 by kBt, e to the power ks. If it has a different, if a particular microstate has a different energy, the probability will be different. Let's call this proportionality constant Z, which is just the sum over all microstates, all accessible microstates of the system, where one of the microstates also will be where it has taken all the energy from the reservoir to here. So this system has extremely high energy, right? But its probability will be extremely low. The probability that all the energy from the reservoir has come here, so this has zero energy and this has all the energy, will be e to the power minus e, which is a very large number, by kBt. So very low probability. And the proportionality constant is called Z, and it is called the partition function. The symbol Z comes from this German Sum or something like that. I don't remember the German name, but that's why it's Z. And it is a sum over, so you're basically calculating the this factor in front. It's e to the power minus beta ei, where the sum is over all microstates, and some set of these microstates will have the same set of energies E, S, and K. Right? The sum is over microstates, not over energy, because large number of microstates will correspond to a particular energy because they can reorganize themselves in phase, in configuration phase space, and more generally in phase space, because all the positions can change, all the momentum can change, as long as the sum of the total energy is EI. And as in the microcanonical ensemble, you have these various copies. So the system, so you can think of it as in time, that okay, the energy is fluctuating as a function of time, and it's accessing all sorts of energy states with probability this much, right? So the probability e to the minus beta E S I upon Z, where I is the ith microstate. And the set of all these microstates belong to a canonical ensemble. So this is the canonical system, where a system can exchange energy with the system. And I want to remind you, this probability depends upon energy by a certain constant, which is the partition function. If we can calculate it, if we know the function of the expression for the energy, you can even calculate it, right? I mean, whether it's possible to do the integration or not is a different, I mean, some or not is a different question, but in principle, you can, right? And I want to highlight that this probability of different microstates is different from 1 by omega, which was true only from a microcanonical ensemble, where all microstates were accessed with equal probability. Here, not all microstates are accessed with equal probability. All the microstates with the same energy, EIS, are accessed with the same probability, right? But if the microstate has a different energy, if this energy system has a different energy, then the probability of accessing that microstate is different. Okay. Does that mean, well, there could be a certain contradiction. If you ask it in class, I'll answer it, but not now. I'll discuss that contradiction when we go on deriving various things. Now, if you, however, ask the question, what is the probability of the system having energy EKS? Then you are going to sum over all the microstates which have the energy EK. And the probability of accessing that the system will be in energy EKS is number of microstates which have energy ESK into e to the power minus beta EKS by Z. Why? Because you have sum over all microstates with energy EKS. I want you to emphasize on the difference between this formula where the system isn't being energy ES and where you sum over all microstates with energy EKS. So you get an extra factor NK here other than this factor. And here, this was the probability of accessing a particular microstate with energy ESI. Here you are asking the system being in energy EKS, right? So I have highlighted this as different from the probability of accessing a particular microstate. Here you are saying what is the probability that the system is in different has energy ESK, and it can be in any of the microstates which has energy EKS. So the probability is much more because you have to sum over the you have to sum over all the cases the probability of those microstates which have energy EKS, right? So NK is the number of microstates with energy EKS. And so I've said that all microstates which have the same energy EKS have the same probability, e to the power minus beta EKS by Z. All right. Now suppose you had to calculate a thermodynamic average. Now, what you do? You could basically, suppose we are looking at the kinetic energy of a certain particle, just as an example of the distribution of velocities of gas molecules. What you could do is basically do a time average, look at the system, the room, see when its energy is E1 and what is the distribution later. It accesses different microstates. After some point in time, its energy changes. It accesses a different set of microstates, and you keep measuring whatever your interest be. Let's look at the kinetic energy of a particular particle, and do a long time average. Wait for millions and zillions of collisions and calculate the total average kinetic energy of that particle, as an example. On the other hand, what you could visually imagine that you have the set of all microstates. Some of these microstates have this energy, some of these microstates have this energy, some of these microstates have that energy. Each of that is like a microcanonical, but the system can actually occupy or access a much larger set of microstates compared when its energy was fixed as E1. So now you consider all those microstates, and if you can take a sum over all microstates with different energy values. So suppose that particle's kinetic energy was I when it was occupying a particular microstate, a different value when it was at a different microstate, right? You sum over all microstates with different values of energy. Some of those microstates have the same energy, and the probability of accessing a microstate is Pi. Then the average value, the thermodynamic average of this value will be Xi, the value of that variable in that microstate, and probability of accessing the microstate, right? And what is the probability of accessing the microstate? E to the power minus beta EI by Z, right? And that's what it is. That's what the average value of that quantity is. Now, it can be some microscopic quantity, like the kinetic energy of a certain particle. It can also be pressure. And of course, I've not written down the expression for the pressure, but I can write it down and I will do it before the midterm. Right? It can be some other quantity, distribution of velocities of gas molecules. Right? So, the distribution you need to calculate for different microstates. Right? So then this will be itself be a function of V. So this partition function, I want to emphasize, is a function of N, V, and T. So when a system is in contact and is in equilibrium with its heat reservoir, and the heat reservoir has a certain temperature, and the temperature will be measured or calculated in terms of microscopic variables. But the reservoir, by default, it comes with the concept of temperature, right? Thermodynamic sense. And of course, that same thermodynamic temperature will be calculated from microscopics. So this Z, the partition function, is a function of N, V, and T. Omega, the number of microstates, was a function of N, V, and E. Now see, because the energy can fluctuate, it is not fixed anymore. Instead, the energy E has been replaced by T. And it can be shown, and it will be shown, that if you take the log of the partition function, which is a function itself of N, V, and T, and multiply it, so free energy is minus kBT ln of the partition function. And that you can calculate only for a system which is in exchanging heat with a reservoir. And if you go to the ensemble picture, you have the canonical ensemble. I mean, okay, we Indians speak of it as ensemble, but I think the French pronunciation is something like ensemble or something like that. I don't know. Okay, so canonical ensemble or ensemble, whatever is the right pronunciation. And this is to be distinguished from as different from S equal to K log omega, which was a function of V, E, and N. And here you took the suitable derivative to calculate T. Here, the free energy that you are getting when you can exchange heat with the environment is a function of N, V, and T. And again, you are going to take a suitable derivatives, del F, del T, which is coming from thermodynamics, to basically calculate minus F, and you're going to take y you related to F, that will come. But at the moment, I'm telling you in the bigger picture that will show that we'll can take suitable derivatives. So F has all the behavior as that of free energy, and let's call it free energy. And then when we take suitable derivative with respect to V, we'll get minus P. And one can also calculate the internal energy, and that can be calculated. This is supposed to be U, not N, and which is the average energy of the system, which will be sum over all microstates, the ESK, sum over all possible microstates, e to the power minus beta ESK by Z, which in turn, this energy can be written in terms of 1 by Z, sum over all microstates, del del beta. I think it should come with a minus sign here, right? Because when you take del del beta, what you will get out here is a minus sign. Right? So I've missed a minus sign here. And here I have missed a minus sign. So 1 by Z, the sum is over all microstates. Beta temperature is fixed. It is not varying. So we can write it minus 1 by Z del del beta sum over e to the power minus beta. Yes, sum over all microstates. And this sum itself is the partition function. So here it will be minus, because it's missing from here, all of these minus 1 by Z del del beta of Z. So that's how you calculate. So once you have access to when you have access to partition function, then you get the free energy, you can calculate the entropy, you can calculate the P, and so on and so forth. So let me summarize. So if you have a system with isolated system with fixed E, V, and N, then the microstates which can be accessed are called uh, realizations of a canonical, microcanonical ensemble. Then what you calculate is the total number of microstates available. And when you take the log and multiply it by suitable KB, then what you get is the entropy, which is a function in turn of E, V, and N, because if you change E, V, and N, omega is going to change. So S is a function of EVN, and then the derived quantities are quantities like T, temperature, pressure, and this is the chemical potential. And all the microstates have equal probability of being accessed. On the other hand, when you have a system with fixed V and N, but the temperature is specified and temperature is that of the reservoir, but the energy can fluctuate, then you don't calculate the total number of microstates. Then what you calculate is something called the partition function, which is the sum over all microstates e to the power minus beta EI. EI is the energy of a particular microstate. Different microstates can have the same energy. All of them have the same probability of being accessed, but what you calculate is the partition function. This sum is over microstates and not energy, right? Because there are a large number of microstates with the same value of energy, and all these microstates are supposed, the set of all these microstates are so-called make the canonical ensemble, and F equal to minus KBT ln Z. I hope I have added the minus sign here. Yeah, so I think the minus sign is there. So F equal to minus KBT ln Z. And once you get the free energy, you can calculate other quantities like E or U. And why can you calculate E or U? Why is it relevant? Because this is an average quantity. This is not an exact quantity. It is fluctuating. And we have to discuss about how much are the fluctuations and so on and so forth. And you can calculate, so you're specifying temperature here. And what you're getting is the average energy, which you identify as the internal energy. And then you can get your pressure, your entropy, your chemical potential. All microstates are not equally probable. Higher energy microstates are accessed with lower probability, and the probability is proportional to e to the power minus beta, beta being 1 by kBt into EI, and the normalization factor is the so-called partition function, which is sum over all microstates e to the power minus beta EI. Right. Just for the sake of completeness, let me also tell that one has also the so-called grand canonical ensemble, which will come, I think, after the midsem, in which you not only allow the energy to fluctuate, but you also allow the total number of particles in the system to fluctuate, which means that your system is not only with the heat reservoir, but also in contact with the particle reservoir, and the total number of particles is fixed, and the total amount of energy reservoir plus system is fixed. And again, we're going to ask what is the condition of equilibrium of system to be with the reservoir, and we will get out the result. We'll calculate certain quantities which we will identify with the chemical potential and temperature, and we'll see that the chemical potential of the reservoir and the temperature of the reservoir has to be equal to that of the chemical potential of the system and the temperature of the system. And the set of all microstates, and of course that will be much larger than that of a canonical ensemble. The set of all microstates are called the grand canonical ensemble. One can calculate something called the grand potential, which is equal to minus kBt ln of Zg, where Zg is now the grand partition function, which is a function of V, mu, and T. And then the things that you calculate out is the average energy, pressure, entropy, and right, and entropy is itself can fluctuate a bit, but the whole system is in equilibrium. And the average number of particles. Now you can't say what the fixed particle, because the energy itself is fluctuating. And we'll show that if the system is large enough, the fluctuations go as 1 by root n. There will be, as n increases, the fluctuations will become extremely low. And that will match with your intuition, because this room has an average energy and the fluctuations about the average energy are extremely low. That's why you can say that room has thermodynamically energy E, right? But there are fluctuations, and we'll calculate that. And the probability of accessing these different microstates is proportional to e to the minus beta ei minus mu ni, where n is the number of particles in your system, and the normalization will be, the grand partition function normalization will be sum over I all microstates, where the energy changes, the number of particle changes, e to the minus beta ei minus mu ni. Depending upon what your convention is, this could appear as minus or plus, depending on the sign convention of chemical potential, how you define it. But in terms of physics wise, that's a matter of convention, plus, minus, but I mean, so this is basically the end. So this will be discussed after the midsem. And the point I want you to take back home, that this is the concept. First, we'll establish this concept, and the rest of the course, which is sometime just before midsem to the end of the midsem, will be applying this formalism to a large class of systems. First, ideal gases, then interacting gases, then magnetic systems, ferromagnetic systems, and then calculating out equations of state. And if you get P in terms of V and T, that is P equal to nRT, if Hamiltonian is right, and if it describes that of an ideal gas. On the other hand, if you had a different system with different degrees of freedom, suppose the degrees of freedom are magnetic spin states, up and down spins of different atoms, and we're not looking at other degrees of freedom, right? Then you can write around a partition function with just the spin degrees of freedom, where of course there is some other degrees of freedom, and corresponding to that you can say, okay, what is the free energy, and then we can calculate other quantities in the presence of a magnetic field, and so on and so forth, and so on. So you can have the entire thermodynamics, except in each case, depending upon whether you are in a microcanonical ensemble, if you are isolated, you're going to calculate the total number of microstates. If you are in a system which is exchanging heat, then you're going to calculate the partition function and relate it to free energy, from which you get other quantities. And if you have a system where both particle numbers and temperature is changing, call it the grand canonical, and you calculate a suitable, you calculate the grand partition function, get the grand free energy, and calculate mean energy and mean, which is the internal energy of the system, and mean number of particles in it, and so on and so forth. So depending upon what the problem is, or what the definition is, what your system is, you're going to use any of these depending upon your convenience. For some simple cases, we'll do it with the ideal gases, and some we'll do it with both. But for more complicated systems, sometimes taking summation over a large number of microstates actually becoming easier. And you can go to choose one of these microstates, one of these ensembles to make your calculation easier. Okay, so with that, I'm going to stop this lecture as well.